Okay, so in this problem, we're going to use the data that was presented to us from Minitab. It's a sample data set, and it's labeled bears. And if we were to look at this data, we would see it contains lots of columns. And this is columns that are representing various measurements in terms of the age, sex, length, width of the head, length, the chest, lots of things, and even the name. And what we're looking at here is this data is collected so that scientists and hunters and whoever else can estimate the weight of a bear using a different measurement. This is important because the weight of a bear is one of the most challenging measures to get. If we are looking at a webcam, if we can make predictions of how long that bear is approximately, and we want to eventually maybe use that to estimate the weight. And that's what we want to do. We want to look to see, using this data, is there a linear relationship or linear correlation between the length of a bear and its weight. So you want to first do that. Then after that, if we make it determine that there is a relationship, we want to estimate the weight of a bear that is 62 inches long. So we have a forest webcam that is estimating a bear is 62 inches long. Can we, using either a regression line potentially or maybe another way, can we estimate the weight of that bear? So there are three things that I want to note here. To determine whether or not there's a linear relationship between them, it might be a good idea just to first get a visual. Get a visual to see a scatter plot of the two variables. So in Minitab, I want to compare, I want to graph with a scatter plot. Just a simple scatter plot for now. This isn't very thorough. We're just looking to see. And we want to compare what variables? Well, we want to compare the weight and we want to compare the length. So that's C8 and C10. Now, which do you think we're going to use as the Y? Remember, the Y variables is what we're using, what we want to predict. X is the predictor. So what are we using to predict? So we're going to be using the length, so that would be our X, to predict the Y, the weight. And from there, we have length as our X, weight as our Y. When you click OK, we get this relationship. That looks pretty good. I mean, that's just a regular scatter plot, but that, although may not be an exact line for sure, that's definitely has a trend that represents a linear relationship. So this is just a basic scatter plot. What we can do now is we can close that. We can do the same thing, create a scatter plot, but with a regression line. We can actually create a linear regression line to help us get this overall trend. So remember, the weight was the Y, the X was the length. When you click OK, we see a longer term trend here. We see a trend line. And we do see that, generally speaking, this line is following the trend of this data. So just by looking visually, the visual looks pretty good. So I'm just going to write good in there. The visual looks pretty good. It doesn't mean, whoops, let me go back. I guess that's okay. The visual is pretty good. Now, we know just by saying something is good by looking at it, that's not statistically sound, that's not mathematically sound. So we know just by visual it looks pretty good. How can we determine or get a measure of that goodness or the strength of that relationship? Well, that's going to be found using the correlation coefficient, which is a measure of the correlation or the linear relationship between these two. So to calculate that, we go to Stat, Basic Statistics, Correlation. What are the variables that we want to test? We want to test C8, the length of the bear, and C10, the weight. Now I do want to display the p-value because that information is going to come back and we're going to be able to use that. So when I click OK, we have a correlation of length and weight of 0.875. So the correlation coefficient is 0.875 and a p-value of all zeros. So I'm going to go back to the p-value and put all zeros in there. We know, looking at the correlation coefficient and the p-value, we're going to use that p-value to actually run a hypothesis test. But the correlation coefficient, as we read about it and saw, that's a very good number. That's a high correlation coefficient. It's relatively close to 1, a lot closer to 1 than it is to 0, which represents a positive correlation, a stronger positive correlation, and a p-value of 0. Well, we've seen p-values associated with hypothesis testing, and we are going to use this. So looking back to your notes, we should note and see from our notes that when we run an hypothesis test for correlation, we have a null and we have an alternative, and there is a Greek letter that we use here in this problem, but I told you it's okay that you write down that the null hypothesis for a correlation coefficient represents that there is no, so there is no correlation. That's what we represent for the null hypothesis, and the alternative is that there is correlation. So this is the null, this is the alternative. This is what we're going to have as our hypothesis test for all correlation coefficients. Now looking at that p-value, it looks like the p-value is 0. The p-value is less than our level of significance. So I'm going to write this. Since the p-value is less than the level of significance, what does that mean in terms of the null and the alternative? The p-value is low, the null has got to go. So we will reject the null hypothesis. That's just a general statement about the null and the alternative. Now let's relate that back to the problem. Well, if we're rejecting the null in favor of the alternative, there is evidence to suggest a linear correlation between the variables length and weight. So there is evidence to support the claim that there is a linear correlation between the two, that there's a linear relationship. We can use a linear relationship to describe these particular variables. Now, that's good. The reason why is because we can now use the length, now that we know that there is a general relationship, a linear relationship between length and width. I keep saying length and width, but I guess it's length and weight. Now that we know that there is a relationship between length and weight, we can use length to predict the weight. In order to do that, we need to find the equation of the regression line. So after making a determination about that relationship, we need to use this length to estimate the weight. So we're going to estimate the weight of a bear that was caught by a cam that had 62 inches long. So it was 62 inches long. We want to estimate its weight. How do we get, using this information, a line? Well, one way is to go back to, if we go into the window, we can go back to the regression line that we made, right? The scatter plot with the regression line. And if you hover your cursor over the blue line, you'll get a box that pops up and it tells you, all right, and I don't want to move it, but this is one way. It tells you that the weight is equal to, and it provides you with an equation. Now, if you can't read that, that's okay. We can actually go into stat, regression, and just regression. The response, this is what we are predicting, and we are predicting weight, and we're predicting it with the length. So we're predicting weight, the predictor, what we're using is length. So when we click OK, we get lots of things here. We get unusual observations, we get the ANOVA, the analysis of variance, which we are not going to be discussing. But up at the top, we get the regression equation. So I'm going to copy that, and I'm going to paste that into the problem here. Whoops. Paste that into the problem, and I'm going to increase the size, and I'm going to bold it. So the regression equation is the weight will be equal to negative 441 plus 10.3 times the length. Whoops, where did it go? There it is. So if we know the length, we can use that to predict the weight. So we're going to do that, right? That's the goal here. We want to predict the weight for a bear that has, or that was seen to be 62 inches long. So we don't know the weight. But I'm going to plug that value of 62 inches. We know that is the length. So I'm going to plug 62 in for length. And we know that there is a little multiplication sign in here, right? There is a multiplication sign in there. Now, just like we would with any other order of operations problem here, we're going to first multiply before we add. So 10.3 times 62 is 638.6. So I just multiplied these two numbers here, 10.3 and 62. And I'm just going to continue to simplify. So the weight, not sure what's happening here with the spacing, but when you add that, negative 441 plus 638.6, we get 197.6. So using our regression line, we found that a good estimate for the weight of a bear that's 62 inches long is 197, and I guess would be pounds. When you're asked to find if there's a linear relationship between these two variables, there's ways that we can approach it. We started very basic by just looking at a visual and determining whether or not there was a longer term trend or a trend line that represented those points, that scatter plot, and we could just visually say it looked pretty good. That's not good enough. We needed to calculate a value that represented the strength of that relationship, which is the correlation coefficient, which we're going to use the letter R. Right? So we already talked about this, but the letter R, we calculated that to be 0.875, which is a good value, and we got a p-value which corresponds with this hypothesis test, and it will always correspond with this null and this alternative. So every time you're given the p-value for the correlation coefficient, that p-value is corresponding to this null and this alternative. The null being there is no correlation, and the alternative that there is a correlation. So again, starting off basic, and then finally this value, this p-value, is suggesting that there is evidence to reject the null. There is evidence to support that there is a correlation, a linear correlation, between these variables of length and weight. Once we have made this decision that there is a regression line that can be used, or there is correlation, we can use Minitab to calculate the best line that describes length and weight. And once we have that, we can use that line to predict values. Now, we're only going to want to use this line, this regression line, if our alternative hypothesis is what we are using. In other words, if back up here we failed to reject, or we decided that there was actually no linear correlation, then down here, using the line of best fit to find and to estimate, that would have been pointless, because up here we would have determined it's not good, don't use it, but then we would. Okay, so the only reason that we use this regression line to make predictions is because the alternative hypothesis is what we found to have evidence with it. So we found that there is correlation, a linear relationship can be used to estimate, so we did that. As you saw in your book, if we found that there was no correlation, we're not going to use a line to represent and predict values, then the best predictor would have been to just find the mean of all the weights, because that would be the best prediction.